these technological trends are definitely positive.
And the real goal was to make a scientific assessment of our observations, or as scientifically as possible, because
That said, by the way, I'm pretty optimistic. I like the technology. I think it's at some point it'll be a game changer, as much just like any technology that had been taking a long time to mature, like nuclear fusion, which is an extreme case.
this whole thing also applies to our computations. And I'm a little bit scared, but also excited about this. Completely new view of how we perform these computations.
I wonder if we underestimate the power of the HPC community and its influence on the market, and that perhaps we really could be more assertive in what our needs are, because that is in fact the future of computing in general.
Silicon photonics could be a great answer to a lot of these problems. To what degree are we likely to get to practical, functional, affordable silicon photonics optical I/O anytime soon?
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hey Shaheen, great to be with you again.
Excellent to be here and super excited about this session.
Yeah, I'm very excited about this one. We have with us Dr. Satoshi Matsuoka, longtime HPC luminary and director of the Riken Center for Computational Science in Japan, and Dr. Torsten Hoefler. He is professor of computer science at ETH Zurich, which is the Swiss Federal Institute of Technology. And the two of them were part of a group of 6 HPC thinkers, technologists, who this month put together a very provocative, thought-provoking paper called The 12 Myths and Legends of HPC. I wrote an article in Inside HPC based on this paper, and we're really pleased to have both of them with us today to talk about some of these myths, legends, but really the issues of technologies, future technologies, and their expected impact on HPC. So why don't we begin with kind of an overall question. I'll turn it over to Satoshi and to Torsten. Is there an overall theme to your Myths and Legends paper? Is it that these technologies have been overhyped, or that expectations have somehow become unrealistic? What is the theme of the piece, would you say?
As you say, these 12 myths are subject matters. Of course, we admit they are of great discussions, of great interest. And, there were a lot of, first I must say, these technological trends are definitely positive. Like, the first myth, the quantum, yes, definitely. We're not anti-quantum at all. In fact, we're pro-quantum, in that it would be an important asset to solve some of the important problems where the traditional computing may not be able to attain. But on the other hand, these various technologies, as you say, have been sort of overhyped beyond their limits. And it's distorting the overall picture of how we should progress as a community, where the investments should be made, how we should be scientifically comparing these methods. And all these things we felt were being somewhat distorted, but this enormous onslaught of these new technologies and advances. So we thought we should step back and, being sort of experts in the area, actually collect the experts in the area, including ourselves. And we really think hard, what are the topics that are, in some cases, oversold, or in some cases, there would be counterpoints or some things we really have to think of to advance the technology, but have not been really thought of. And then, really make it a fun paper, because then people will read it and we'll start discussions on these important topics.
Yeah, I would completely agree and go further and say that somehow felt the responsibility that we had to manage the hype that was created along some of those in those areas. And basically to avoid the disappointment and potential collapse of these extremely important fields that Satoshi just outlined. And so we have actually watched each other that we give various talks. So I watched Satoshi giving talks about these things, and he watched me giving talks about these things. And at some point we were just like, hey, we have to get together and write this down. This would make sense. And we finally got it done over the Christmas holidays, essentially last year. And the real goal was to make a scientific assessment of our observations, or as scientifically as possible, because as you see in the paper, some are semi-religious discussions. So you cannot really have a scientific assessment, but you can at least outline scientific pros and cons and then have the community discuss. And this is what we wanted to start, a community discussion.
I think that's excellent. And I do believe the paper has been successful in achieving its objective of causing discussions I thought it was written quite skillfully, such that it was enjoyable and provocative without really being too blunt of an instrument. And and of course, some of the topics that you bring are very important in a very visible and public way, like it wasn't the case 20, 30 years ago. And that brings in attention to those topics by people who are far away from the expertise that is required to have an assessment. And then at the same time, we have learned how to monetize these new technologies as a society. And all the startups have an interest in obviously being optimistic. And that fine line between optimism and overhype, the fine line between the enthusiasm that you need to make progress, but the realistic approach that you would have to be credible. That's a tension there. How would you see that?
Well, at least my reaction when somebody pointed out on Twitter, there are a lot of startups that may be precisely hyping some of those points. And then my reaction was, well, if this article is widespread read by the people who are investors or at least advisors who are making advices to these investors, then they will really have to answer some tough questions. Right, because now the salient discussion points with regards to these new technologies is brought at the open will become even more argumentative with the community discussion going on. So this will certainly allow the people who are trying to make these decisions or trying to foster technology also be able to ask these very hard questions regarding some of the limitations of these technologies and evolutions of it.
Yeah, exactly. I mean, these questions are actually super important. I think if I would have to name the major contribution that we try to make is to help people define these questions and help all kinds of people define these questions, like investors, young students who may be confused, and also the people developing the technology themselves, and also the people who publish these weird, these somewhat exaggerated statements, that they could even reality check themselves a little bit and be realistic. So it's really about these questions that Satoshi mentioned that we try to define.
I thought another really valuable aspect throughout the article is that you give a very realistic analysis of the barriers that remain for these technologies. And so some of these technologies I've written about, and, I talk with the vendors, but of course they're going to emphasize the upside, the optimistic side. They're not going to talk about the potential barriers more than they need to. So I think you all really highlighting that is a very valuable service for everyone involved. The other aspect I really liked was that, and it kind of relates to the hype idea, is not to get too caught up on any one particular technology as something of a panacea for HPC challenges. What you all really emphasize is this, to quote you, the intricate relationship between the application requirements and the system capabilities in terms of balance. And sort of starting with the workload, starting with the requirements and working backwards toward the system and its components from there. I thought that was a very valuable theme too.
So one question I have, what do you think is the most controversial, the most important question?
Let's start with the overall theme.
Yes.
For example, when the Apollo went to the moon, some even 50 years ago, over 50 years ago, the engineering was done such that we knew how much energy it would take given certain payloads, and then all the engineering was done to basically realize all these parameters which are intricately intertwined. And of course, there's a lot of engineering done to mitigate some dangers and risks. And so it was a very comprehensive engineering effort involving tens of thousands of people. So this is very, very careful engineering in order to be able, and there are a lot of innovations, granted, but at the end of the day, the objective, and there wasn't really hyping involved, because if there were just hype, we would not have gone to the moon. So, HPC, similar with HPC, I mean, what do we do HPC for? Well, one is to advance IT and the technology, but other is to solve real world important problems, because otherwise we would not exist. The importance of HPC in the society, growing. So in some sense, we're responsible in order to make progressions. We should always be cognizant of the objectives. And once we are out there to solve these problems, we should really be honest about what are the pros, what are the cons, what are technologies that need to be combined to come up with a solution. So, we need to live in both worlds. On one hand, we need to be innovative. On the other hand, we need to do careful engineering assessment to reach our objective. We really need to think about what are we good for.
The role of HPC, in my view, and of course, I am biased like many of us are, but while I hear that HPC is not a very large market and it's not in a position to be in the driver's seat of the IT technology as a whole. It nevertheless, traditionally and in the future, to me, is the only part that is going to be growing nonlinearly and more than with GDP or more than with population growth. And as a result, I think that my observation is that every company, every organization that starts out with IT eventually ends up with HPC. Look at the cloud guys, right? They had no interest in HPC for a good long while. And now increasingly, the only part of the application that is growing exponentially and is using like thousands of CPUs at the same time is going to be HPC. So I wonder if we underestimate the power of the HPC community and its influence on the market, and that perhaps we really could be more assertive in what our needs are, because that is in fact the future of computing in general. Well, what do you think about that?
I would say that you're probably absolutely right. Many people underestimate HPC's innovative potential. I usually, in my lecture, I call HPC the Formula One of computing. So we actually are a very risk-taking community in order to achieve the highest computation that people do anywhere on the planet. So we invent all kinds of new things. After all, the deep learning revolution was basically driven by a success coming out of HPC. And you can even hear the Turing Award winners,
right,
Geoffrey Hinton, say these things publicly. So he called it the advance of compute, but at the end, GPUs were mainly driven by the HPC market, the general purpose GPUs. And we keep driving this. I mean, vectors come out of HPC originally, now are in every single laptop. Same with GPU computation. Tensor cores will be universal, even though we may be disagreeing on this call. And so we are driving the future in many regards, because the performance of the largest systems today is going to drive the normal system tomorrow, and is going to drive my watch in 5 years, or maybe 10 years.
Maybe 30. Yeah.
Maybe 30. Well, actually, my watch is quite fast. I mean, I have 4 cores. So.
Yeah, exactly. Yes.
Yeah, you're
I don't
smart.
know what watch I have.
Yeah, these are great points. And now one thing I've chatted about with Satoshi is, I think increasingly with more frequency, we're going to see the things that are coming out of HPC and big AI, if we combine those two, really breaking out into public discussion, public notice, major news. And the most recent example is Chat GPT, but that really comes out of HPC AI. But by the same token, I'm amazed by how many friends of mine who are generally well-informed people, they're relatively tech savvy, have never heard of NVIDIA. I've never heard of TSMC. It's pretty amazing. For us inside of the HPC community, it's hard to have that perspective on where do we stand in the general awareness, general knowledge, if you will, of technology. But what if we got into, now I know, Shaheen, you looked at the 12 myths and kind of categorized them a little bit, broke them into groups.
Yeah, let me paint the picture that I could walk away with. And as I was saying in our pre-call, this may or may not be approved by you guys, but I saw a few topics that were sort of new technologies that are still evolving in various stages of proving themselves and understanding where they work and where they don't and how. And that's quantum computing, AI, and to some extent cloud computing, and the role that it might or might not play in HPC. The second one was just HPC systems and the different aspects of a system, from specialization and composability to accelerators, memory per core, mixed precision, although there's obviously overlap. The next one was really the future of HPC, and that's singularly the zeta scale, which I think is a useful thought process, but perhaps not much more. And then the next one is applications. How do we optimize applications? What is the development environment? And that alludes to application performance and Fortran and some of the very good questions that you raise after each myth. So we could take that path and see where we want to take this next.
No, I think for the first one, as you had described earlier, there's a fine line between sort of a innovative new topic, which are of course valuable, and that's why the research and development are going on, versus overclaiming this as hype, and so it's a panacea for everything. But that tends to happen. Of course, we want the technology, whatever being developed, to be widely applicable as possible. I mean, there's always a desire for any like quantum AI. There should be research to try to see if it's applicable to certain problem domains that it had not been applied to. For example, there are a lot of research going on right now to see if some of the first principle PD solvers can be sort of augmented by deep learning surrogates. So, yeah, I mean, that kind of research is certainly positive. Some of the research being done are really excellent in that regard, trying to mix for example, in AI, trying to mix circuits and precise PD calculations. That has led to some big innovations. But that said, there's a tendency that without proper assessment and limitations that should be made, and in many cases, of course, people try to make these clear. There are good authors, there are good researchers. They try to expose in a real scientific paper. They try to expose the limitations, the errors, and those things because that's what you ought to do when you're a scientist. Oftentimes, this gets sort of, for some reason, the negatives disappear. And then the whole hype about, like quantum will replace all the supercomputers that we know. So oftentimes I'm responsible for one of the biggest supercomputers in the world. And we continue on a trajectory towards trying to design the next one. But, I will often get the question from the press saying, well, you're working on supercomputers and you achieved this and this with Fugaku. That's great. But the quantum computer's coming, it's going to subsume everything. And why do you even bother working on traditional supercomputers when quantum will take over? I mean, directly from people like it from the press. Yeah. No, sorry, but I'm not trying to. Yeah,
well, I would never ask you that, but go ahead.
Yeah. So, but then you wonder, you don't blame the press people themselves because they must have gotten this misconception from somewhere. And we try to kind of poke into the sources of how this conception kind of came about and the thoughts. What were the process? What were the flow of information that actually led to this? And how can we prevent that? And the only way, not the only way, but the good way we thought was really to expose the fact that these misconceptions are being widespread in some cases. And the two things is to really think about, not only to think about how, not just to complain that there are misconceptions, really get to the bottom of how we can solve these misconceptions. And the only way we can think of solving these misconceptions is really propagate the idea that not only to propagate the idea that these are misconceptions, any new technology has to have a really hard-line evaluation phase to see if what is it credible for and what it's not good for, and then make a very deep scientific assessment of it. And we want to make that really a part of engineering. As I said, as the way we went to the moon, we're very honest. When you need technology, we should step back and be very honest about it. We should make that very much a part of our discipline.
Well, let's take the case of quantum. What would you say? I guess the point about hype and high expectations that are driven too high is that when expectations aren't met, then interest is lost, investment can go away, funding, and then you can move into, and we saw this over the years with AI, these AI winters where people just sort of gave up on the idea. Now, of course, it's here to stay. I think everybody agrees with that. But that could happen with quantum. I mean, my own feeling is there's so much work being done globally on quantum. I'd be surprised if we go into a quantum winter, but we could go into a period of abeyance where people are just saying this stuff isn't coming along fast enough because their expectations were too high. What would you say are the biggest barriers, biggest challenges in quantum right now on the technical level?
I think quantum really needs some guidance on the algorithmic side. You mentioned that we may be disappointed because it comes too slow. But I would actually go even in a more extreme direction. We may also be disappointed if it comes too fast. Let's assume a quantum computer actually shows up tomorrow. And by that, I mean a reasonable quantum computer. So not one that runs at multiple gigahertz, but one that runs at multiple megahertz because of quantum error correction and all the details that we could talk long about. But let me just skip those. And that computer showing up tomorrow, which would now be a likely computer, would actually have a challenge because it would not outperform HPC systems on most of the quantum algorithms that we know today. Because for decades, algorithmic researchers have only looked at asymptotic speedup. So they were super happy to get quadratic speedup for something. But if you run at a megahertz, a quadratic speedup will not get you very far compared to a supercomputer where thousands of processors are running at gigahertz. So that's one problem. And we actually, specifically together with Microsoft and Matthias Treuer there, we have a paper that's going to come out and does very detailed analysis of a candidate quantum computer that we believe is very likely, and that's coming out in communications of the ACM. That was kind of the inspiration for that first point, that first myth. And what we really wanted to achieve is navigate or moderate that hype, but as a more important goal is to tell the community that there is a huge opportunity to invest into new quantum algorithms for problems that are not just Grover's so-called database search, even though that is like the worst name you can imagine, because you can't search a database with a quantum computer faster than with a normal computer, and there's so many reasons.
I would say you cannot search it at all.
Well, you can, but it's going to be super slow. I mean, after all, your quantum computer can do anything that a normal computer does, right? But mega
I
slow.
think a spreadsheet, maybe. A database, no.
Well, if you can read it, right? So yeah, that's the argument on the quantum. So really, it's an opportunity that we need to help policymakers also to help them make decisions where to invest.
So one challenge here is that these technologies are becoming so important and so fateful for politicians and countries and organizations that they feel like they cannot afford not to have a seat at the table. They cannot afford not to invest, almost regardless of if the likelihood of success is more than zero, they're in. Because if they miss out, it will be disastrous. And I think that's one reason why money continues to get poured into this area, which actually is a very positive thing because it will accelerate development. But also it adds to the hype and it sort of positions you closer to the quantum winter that we averted last year, but we are definitely not immune to. That's really hard problem to solve, is that when it seems almost like that the investment model has shifted for some of these technologies.
Certainly, we should invest in technologies that are, if they pan out, become very important. Even if they're low risk, then there should be lots of thousand flowers bloom. That's what the basic research should be about. Because or any like venture startups, venture startups have very low rate of success, and we accept that. Basic research has very low chance of success, and we accept that. As an investment, and maybe 1 in 100, 1 in 1,000, they're successful, and the outcome may be game changing. So if the expectation of the investments are set in the correct way, and then there's an evaluation process by which all these new ideas are evaluated. Just like Torsten said, there's been lots of proposals, quantum computers, and also quantum algorithms and so forth. There are a lot of studies being done at every aspect. But at the end, there hasn't been as much research on predicting how many we can solve these types of problems, assuming that we have this number of qubits, and by the way, error-corrected qubits, and also at running at certain frequency. And then at this point, there'll be a proper quantum supremacy for these important problems in quantum chemistry. So Torsten's group is there are several groups doing that. And the Torsten group is one of at Microsoft, Matthias, one of the few groups in the world that's actually really serious about this and publishing papers about this. Again, these kinds of assessments as scientists, we're supposed to make. But oftentimes, we just present certain ideas. Oh, it's good for this, and this is good for that. As such, this must be good for everything else in the world. So those are types of, even scientists tend to make these types of claims in their papers, or not, at least not do proper assessment. And this really leads to the hype. So again, I'm not blaming any particular individuals or press or politicians and so forth. Just the whole framework of not being able to do the proper assessment and being able to communicate these assessments properly to the people who are making investments. Sure, they may. I'm not blaming them for making assessments into risky things, but if they make investments, they should be told, right, whether it's good or not, proper technological way. And the lack of that is actually creating all these hypes.
Do you feel it is possible to have a standard for such assessments that is not going to itself be criticized by those with an agenda or with a misconception? Because that's the other problem in these days that we live in, is that no truth is beyond challenge.
Well, that's the whole point. What HPC had been very good at. HPC is a very competitive community. What other communities have standardized benchmarks that would compare all the machines in the world, like top 500 HPCG in IT? Not many, right? Yeah. So in HPC, we're supposed to be good at that and making these candidate assessments of the technologies we have. So the concern was, despite our excellence, there are all these hypes coming up that are starting to, in some sense, starting to tarnish some of our reputations of being a community with ability to do candidate assessments of our abilities.
That's a really important insight, and I'm really glad that we, managed to get to a point where, I could hear it from you. Thank you.
Now, Shaheen, is there, besides quantum, what would be another one of these issues that's in that grouping?
All right, but let's do AI, because AI is another topic that is simultaneously, I think, like quantum, overhyped and underestimated simultaneously. And it is hard to understand what actually works when, and it's having such ripple impact on HPC, as you mentioned, Torsten, and I would totally be in that camp. I believe HPC enabled AI and took it out of its AI winter that it was in for a few decades. But now we are where we are, and it is now a tool for HPC as well as being enabled by HPC. How do you guys see it evolving?
And it's actually getting more interesting because you could argue that HPC enabled AI, but it may eat its children.
The Darwinian mistake.
Because what's likely going to happen is that AI is already a bigger market than HPC, I would say, and it will drive the development of future architectures in a way that HPC has to follow. For example, this low precision business, right? So we could argue that in a couple of years we will have only negligible FP64 performance on our chips, and that's going to be a problem for many.
Well, already the Biren chip that was announced does not have 64-bit.
Yeah, exactly. Well, you can always emulate it with a couple of FP32 instructions, but that's what I mean by non-negligible performance.
Well, isn't that how we got into 64-bit to begin with? Is because the simulation was too slow and we couldn't get a way to get better accuracy, so why not just do it in hardware?
Exactly, but at the time, we didn't have these AI tools that may actually solve parts of the simulation business. So we could hope that we could learn better representations for PDEs, as Satoshi mentioned, in a data-driven way that can deal with lower precision, but we don't know whether that works yet, or at least I don't know. And so that is something super exciting to be explored, and that could change the way we do HPC. That has a huge potential in my view.
Yeah. Satoshi, what is your view on this?
Well, firstly, I don't think AI and HPC in terms of, first principle solvers like PDE are antagonists at all. I mean, there are just different ways of solving problems. So certainly solving PDEs by first principles is more of a deductive type of, traditionally deductive type of science approach, whereas AI is inductive. You learn. And both have its advantage and disadvantage, and sometimes, in many cases, in fact, if you combine them, they become more powerful. So there's a work, for example, at the Earthquakes Institute at University of Tokyo, led by Professor Ichimura and his group, and that they were able to achieve, on Fugaku, they achieved 1,000 times speed up over K, which would be equivalent to something like a 10 exascale compute that they had wished they would be able to do in order to do proper assessment of the earthquake. Now, of course, Fugaku is not 10 exascale. It's only half exaflop on Limpact. So how did they achieve this 10 exaflop worth of computing? Well, this is by combining the two approaches in a very clever way. And I won't go into details, and if you're interested, you can read our paper. But they have a very clever way of combining the inductive methods, the AI-based methods, and PDE-based methods in a way such that you retain the precision as if it had been computed with fully PDE approach, but much faster, part of it being much faster by acceleration by this AI method. So the combination of both approaches will certainly, there's a huge opportunity for new types of approaches and algorithms to advance our compute. And I think we're only starting to scratch the surface. Well, that said, the downside is to say, well, because of the commercial importance of AI, the HPC there'll be degenerative effect on HPC. With the growth of AI, the overall speed up, the hardware acceleration is ever increasing. Now there are some salient points where precisions, in particular numerical representation in particular, but part of which may not suit the traditional HPC algorithm. There are some simple solutions like Torsten said, you can combine multiple 32 bits to perform 64 bits, etc. And there are very good work in the area to not lose performance while you're doing that. But that's sort of a solving stuff at the low level. I think rather the HPC community should really think about this AI plus these new hardware, the acceleration achieved by these new hardware, which will actually accelerate both in many cases as a new weaponry to go beyond the current, the exascale, and may be able to achieve effective zeta scale performance without really going to the data scale impact.
One thing about mixed precision that is a question is that as we look at future chips that are tiles and chiplets, and you can envision that you look at a menu of IP and you can say, I want 3 of these and 2 of those and 1 of these, go lay it out on a substrate for me and give me my own custom chip that is going to cost the same, as essentially the volume requirement becomes less of an issue. Could we see a future where you actually can have the cake and eat it too? And you say, you know what, I do need some 64-bit, but not a lot. And maybe for HPC, for this particular system, we can have a configuration that provides that, but we have a more ideal balance of what capabilities we need on a chip. If that sort of flexibility comes forward, then maybe we can have the cake and eat it too. How do you see that?
I would go even beyond that. I will go further, because one of our papers, and we written a couple of years, 2 or 3 years ago, wrote a couple of papers, and these papers also became motivation writing this particular paper we're talking about, the myth paper, is the fact that there haven't been too well-studied assessments of the true need of things like precision. Certainly, there have been work on at the very theoretical aspects of precision, and certainly people may have said, well, you just use 64 bits in my program, and I don't want to rewrite it to saying like the C program, let's say double to float, and because I don't know the consequences. Well, no, not that type of thing, but really to assess the true need of these high precision in what type of application, what's the application mix, and what are the future technological advances that would allow basically, make these reliance on FP64 be rather negligible. So despite the rigor of our discipline, we found that these types of assessment, that the need for, what's the true need for 64 bits? Do you really need 64 bits? I mean, is it really true? I mean, you may need it, like in a PDE solver. It's all memory bound. So you may need 64 bits, but not very often. And since you don't need it often, you can even emulate it. It's going to be negligible performance implication on your program. So why do you bother having that in the hardware in the first place? That's a very simple assessment. So those types of rigorous assessment of the true needs of respective parts of hardware, it turns out there is not disciplined way of having done the comprehensive studies of covering all those. Yeah. So that's something we really should do before we go saying, mixed precision is important or not.
I see. Torsten, you were about to say?
Yeah, I mean, this is a super interesting discussion. I think I have an anecdote here that Satoshi was mentioning. So when I arrived in Switzerland, everybody was running the local weather simulation in FP64. And I was always wondering, why are we doing this? Like we're throwing a factor of 2 on the floor and we don't really know. But this was just pure conservatism. And it took 3 years of lobbying and various implementation demos before now the production weather forecast in Switzerland is running at 32 bits. And Meteo Schweiz and Oliver Fuhrer was mainly involved there. And so they actually agreed. And now the question is, can you go further down? And we tried to show that analytically. Of course, we are scientists, right? That's what we have to do. Like Satoshi mentioned, we found that actually 32 bits in the worst case is actually required if you want to run about a 1 kilometer resolution model. So that's a problem. However, that's the worst case. So do we care about the worst case? Well, generally in deep learning, we don't. We know in deep learning that the dynamic range of FP16 at least is actually required to faithfully represent all the activations and weights in a model. However, in the average case, we can quantize things down to a couple of bits, even 2.53 bits, like we just showed in the GPT-Q paper for large generative models. So now the question is, what do we do? Like we can do worst case analysis, but that doesn't tell us much. And then we typically revert, and that's what the weather people did. They revert to experiments. Like they just show, for our input, for what we usually see, 32 bits are enough. That's good. And so now we have a problem, right? So the scientific approach has to give way to some kind of empirical evidence that we keep accumulating.
This is
interesting. And that is where deep learning is coming in, right? In deep learning, it's all about the expectation. Like there's no worst case proof in deep learning. We all know these models can be arbitrarily bad. And now this whole thing also applies to our computations. And I'm a little bit scared, but also excited about this completely new view of how we perform these computations.
So you're saying that we, people like me, have been naively going about for the past decades thinking that there was some proper error propagation analysis done.
Yes.
where we kind of prove that we need a minimum of 53 bits and therefore we have to use 64. That's not the case, you're saying.
Exactly. And what the other observation I made is actually people were very hesitant to accept really convincing the climate folks was very painful because they made exactly the arguments you mentioned. But then the machine learning revolution just happened and they were watching other computations going lower and lower and lower just empirically. And then suddenly they thought, hey, maybe we should try that as well. And they did. And it worked. That's
right. Well, the other thread in your comment is that, I asked Rick Stevens this, is that are we going from an era where we were used to precision to an era where we better get used to probabilities?
Yes.
Because with quantum and AI, they're all sort of, well, it's close enough by 99% or 98%. Is that another thing that's happening?
Absolutely. And there's one problem, actually. The Turing Award winner, John Hopcroft, was pointing this out in a keynote at the Korean AI Summit, where I was in December. That was very impressive because he said we are lacking the education in statistics.
Yeah.
So most humans have a really bad intuition when it comes to statistics, including myself. And he was arguing for completely replacing our education to make statistics a basic like algebra, the first thing you learn, which is not the case today. So I completely agree with you. We go into a probabilistic view of the world, but we are not ready for it.
No, we're not ready for it. Yeah. Also, I'm delighted to hear John Hopcroft's name because he was my professor and he was very difficult.
Maybe you're not so delighted, actually, Shane.
Oh, no, I am super delighted. I felt honored to be in his class.
Can I move on to your disaggregated myth, which the central focus was on silicon photonics? My general sense is that traditional copper-based I/O is kind of a lagging component within HPC, that it's really becoming overburdened. Data movement bottlenecks are creating tremendous problems across system architectures, and that silicon photonics could be a great answer to a lot of these problems. But your analysis of the barriers that remain with silicon photonics, if you could put that into context, I mean, to what degree are we likely to get to practical, functional, affordable silicon photonics optical I/O anytime soon?
Well, silicon photonics has always been technology that would enable 5 years from now.
Yeah.
That said, by the way, I'm pretty optimistic. I like the technology. I think it's at some point it'll be a game changer, as much just like any technology that has been taking a long time to mature, like nuclear fusion, which is an extreme case. But you're right in saying that now what will happen is our ability to manufacture silicon in a way such that we will be exploiting 3D, we'll be exploiting various types of new types of transistor structures and all that stuff. Will amplify and grow the ability to move data within a chip or maybe adjacent chiplets and so forth by a significant amount. And in fact, that's necessary because that's where we expect the performance gains to be attained in many cases. Because I think Torsten also wrote a paper like the world is going sparse, even in deep learning. Any sparse structures, you need data movement. Right? So, and totally agree about that. Okay, so it's all good within a chip. But then once you go outside, the discrepancy, this immense ability to move the data in proximity in silicon or just any sort of bonding between silicons versus something that's geographically far apart, even a meter, will be enormous. There'll be such orders of magnitude difference between those that's at a point there will be a sort of a transition where there will be a mandate to move to silicon photonics rather than people saying this is a cool technology. The question then is when is that? Have we made the proper technological assessment to say, okay, when we get to this bandwidth in the system and we run these application portfolio, we go to this kind of structure in our architecture, we have these types of bandwidth requirements in our algorithms, at which point then we will need to move to silicon photonics, not by the rule of thumb. And as far as I know, we have not quite made that proper assessment. And that's why silicon photonics, to me, seems technology so close, but yes, so far.
Yeah, and going one up from the silicon photonics to the disaggregation, actually back to the questions that we tried to help the community ask. here in this case, the question should be all about the 3 L's: latency, latency, and latency.
Yeah.
Can you actually, in a disaggregated system, can you deal with the latency? Because I agree, silicon photonics is great. It'll probably come. It'll probably get us an extreme amount of very cheap bandwidth, but there is always the speed of light. And the speed of light is a problem. People are inventing hollow core fibers just to get closer to the speed of light, but you cannot beat it. And so that is one of the major questions you need to ask there. And the answer is going to be painful.
Oh, yeah, I totally agree about that. And that kind of alludes to the other section where we try to categorize the applications in terms of what are the principal component of the algorithm that's the speed that the execution performance is bound by. Is it the compute? Is it the bandwidth? Is it the latency? And of course, it's not as simple as that, actually. When you do try to do real performance models, these actually do combine at various levels. So when we make these assessments about the requirements, we really should be honest, again, be very honestly scientific about these things. In order to say, well, here's the latency target we cannot overcome, even with the most cleverest of software and things. And then as such, here's an asymptotic limit as to how much we can, provide speed up to these algorithms, as long as we stick with one algorithm. And then, here's a limitation, and then is your silicon photonics worth it? Or we have to make some algorithmic innovations in order to avert these. For example, if the latency problem, the other alternative way is to change your algorithm so that you'll be less latency now. So you have to think about these things in a very holistic way.
Excellent.
I did want to get to zettascale, and I think your prediction was 2036 or 38, extrapolating on how the previous milestones have taken to achieve. So that's a pretty interesting finding. But in any case, we'll just thank both of you, Satoshi and Torsten, for joining us today. Fascinating discussion. We encourage everybody to check out this paper. If you look up my article on Inside HPC about the 12 myths of HPC, you'll see links to the scholarly site where the paper exists. So thanks very much.
Yeah, what a pleasure. Thank you very much, both of you. And I really look forward to additional discussions when we can get on your calendar.
Thank you.
Catch us in hallways, and we'll be very happy to chat. Thank you.
Exactly.
I look forward to it. Thank you.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comments section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.